Hi again, this is John from Optics for Hire. With me is Sergey Sidorovich, an optical engineer at Optics for Hire. And we're going to talk about the work of optical engineers today, specifically an analysis of a temperature probe using far infrared 10 micron wavelength energy. Hi, Sergey.
Hi, John.
Good to see you again. If you're interested in optical engineering content, please like and subscribe. And don't forget to comment below. We always appreciate hearing from you, and it helps the algorithm. Thanks. So this is a project that you worked on maybe about 10 years ago.
Yeah.
And we were helping our customer figure out what was the optimal design for this temperature sensor that had a probe that went down sort of a tube-shaped pipe with fiber. And then after the fiber, there was some collection optics in the sensor. And we were trying to figure out in the tip at the distal end of the fiber what kind of optics should be used to collect the thermal wavelengths of light. So you wanted to look at two different designs, what their efficiency was given different conditions and field of views. It was quite a complex program, but let's jump into it and hear what your recollection is of this system. So tell us about what we're seeing in this first image. This is kind of a basic 3D model of what they were using, right? And what is this part here?
This is a virtual optical model that we made in Zemax, and this is the system that collects heat radiation or radiation that burns because of heating, and focus this radiation at the sensor. So this gray tube is the end of the sensor that can be put inside the tube, and you can see a cutout from this gray tube, and this is a enter window. This part is used for the radiation collection. Then the radiation reflected by the prism and into the fiber, but we cannot see the fiber in this model. I removed the fiber to make simulations faster, and these lens assembly are placed, they can placed on some distance, long distance from this gray tube, and this assembly contains 4 lenses. They should be very cold to not burn any noises for the sensor, and at the far end in this in this slide, somewhere there, the sensor is placed.
So there's heat here. It comes through this little cutout. It hits this prism, maybe reflects off this surface of the prism into the fiber through the tube of some, unknown length, and then these are collecting optics at the end of the fiber, which you pointed out have to be cooled because you don't want to have wrong information based on some heat.
Yeah.
And then over here on the far end is the photo, is the lens, the camera, the sensor. And then we have a slightly different architecture here. This one is not a prism, but an aspheric mirror. So the light again comes through this tube. There's a cutout, but this is a different optic.
Yes, you can see that cutout became smaller, and it looks like the spherical mirror is closer to the aperture, to the fiber end. And we, in first slide, we used some optical element. I don't remember exactly. Probably it was made from zinc selenide material for this infrared region. And new lens use reflective surface. This is because it is easier to produce a spherical surface, not like this, but like in the second image.
So in the prism one, the light actually enters the optic. In this one, there's this aspherical mirror which it reflects off the optic. So it doesn't.
Yeah.
Okay. All right. So we're going to look at what your simulation showed in a second. But first, this is more about your layout. So the object distance, which in this case I guess is heat, right, or the location of the heat. The location of the heat could be different. We didn't know, and so you're going to look at if there was some heated object at each of these distances, how would that change the performance of each?
Not even location. We do not exact placement of the heating, and we don't know the form of the heating, its area or volume that was heated in some reason, and we need to understand how the signal changes depending on different distances of the heated area from the sensor.
Because it could be a small spot, could be a larger spot, could be uniform.
You need to understand.
Yeah.
Where is it?
where is it at different distances? Yeah. Okay. All right. So this first bunch of images, you have the focusing lens and a window. So where in this layout is the what you call the window? You said distance between the focusing lens and the window is 5.2 millimeters.
This is a good question.
If you don't remember, it's okay.
I don't remember.
Okay. And this is what we're calling the focusing, or this is what we're calling which is the focusing lens. This is the focusing lens. The optics outside on the other side of the fiber.
I don't remember exactly.
Okay, I think it is. All right. So now we're looking at your first case here where we have an object. It's 1.5 millimeters away from the exit aperture of the prism, and you've put some sort of known heat spot, I guess.
No.
No? Okay. How did you make
this? This is more interesting process. We need to define what area can be seen through all this optical system. This is why.
As I see it, this image gets smaller as we go through different distances. And that makes sense, right? Because as the object moves away, we're seeing a larger area.
This is not object distances. I don't remember exactly, John. I don't want to lie. As I remember correctly, we used the whole object distance area to generate rays.
Okay.
And then the area that you see, this area is seen by the sensor that is placed near the lenses. And this is an image of this area that is seen through the system. So at distance 2.5 millimeters, the area that's visible for the sensor here is it.
Just this small part, right? So this whole blue detector, as I see it, is 6 millimeters by 6 millimeters. That's this blue box.
Yes.
And that's an area that the whole thing is actually heated.
Yes, and only this small area is seen.
But only a small percentage of it, only this here we have it. So it's -3 so only
about millimeter.
Yeah, about a millimeter, a little more than a millimeter is going to be seen through that prism detector. And then as we go to bigger object distances, again, this whole 6 by 6 area is actually radiating
even
heat,
smaller.
But now we're seeing
half of millimeter,
even less. And then as we move the object distance away, of course, it's getting even smaller. And then you did a separate analysis, again in Zmax, again using the prism lens concept, but you changed this distance between the focusing lens and the window, which I believe is on the exit side, close to the sensor. And what do we see here? We see
wider field of view.
Slightly wide, but not a lot wider field of view, do we? We see
almost twice.
Okay, well, hang on a second. This is 1.5 millimeters, and I'm seeing 0.6 to 0.6. And now when we switch,
not twice, yeah.
It's a little noisier too. It's somewhat similar, but it's a little bit noisier, I would say, which I don't know if we have an explanation of that. Do you recall why there might have been noisier there at the top?
Probably it is because of a smaller amount of rays were achieved to the sensor, and efficiency is lower in this case.
And then, I mean, some of these Zmax simulations, there can be artifacts that are based on the number of rays that you picked for your simulation, right? Like you could, so you have to know when to ignore noise, because it's really just the fact that, you used 100,000 rays instead of 10 million rays or something like that. Okay, so then as we go farther, the same thing happens. We're seeing smaller and smaller portions of the field of view, and with the prism system as you move the object distance to farther points away. Essentially, I don't know if this was an artifact either, but this is sort of an interesting how the detector is at this distance when the object is 5 millimeters away. It's kind of a different shape and different, spot pattern.
In reality, the sensor does not see this image. It simply collects the radiation and
overall radiation.
Yeah, in this case, we need to understand that efficiency of the light collection, of the radiation collection in the center is higher than at the edges.
Got it. Because we don't really care about. We just care about the total amount of heat. So
yeah, it's described.
Yeah, we're not creating an image. We're just collecting heat. And now we have the second kind of architecture for the tip, which is this aspheric mirror. And again, we have a slightly different spot shape. And if I'm reading it correctly, the detector size is the same. It's a rounded shape, but the area that it's collecting is fairly comparable, I would say, right? It's plus minus 0.6 to 0.6, so
Yes.
plus 6. Now, here's where it gets interesting, because in this case, as you're moving the object distance farther away, we actually see that the simulations indicate that we'll be collecting from a larger area. So our sort of field of view is increasing with the aspherical mirror concept rather than reducing as it was in the prism mirror. Am I reading that correctly?
Now the field of view is bigger, yeah.
So that potentially is advantageous. So now that we're at 7.5 millimeters, we have 2.4 millimeter full field of view, whereas with the other one it was, a quarter of that. And then here you've changed the focusing lens and window distance, and we still see the same story repeat itself, which is that the field of view gets much larger. And in this case, when that parameter is changed, it gets to be almost not quite 4 millimeters, 3.6 millimeters field of view.
But amount of energy is higher. Total power collected by the spot is higher.
And the total power collected is more, you're saying?
Yeah.
Okay. So let's look at your summary here with the distance between the focusing lens and the window, which maybe that's the sensor window. And with the prism lens, when it's close, it's collecting from a larger field of view, or similar, almost the same. But what we were just saying, you can see with the prism lens, the field of view is 0.35 or 0.7 millimeters, depending on that focusing lens, but it's much, much larger with the aspherical mirror concept. And you're noting here the light spot is measured full width at half max. Now, the other thing that you were looking at, which we didn't talk too much about, is the total amount of light collected. So I guess we would call that efficiency. And the prism lens is collecting about half as much light as the aspherical mirror from both distances. So I don't remember where we went with the product or the project, but based on this report and your simulations, it looks like the aspherical mirror concept was a clear winner. Is that right?
Yeah, the project was completed by the full redesign of the system.
This was a report from the very start, when we were just kind of thinking about what different concepts we should implement to collect as much heat radiation as possible from the largest area as possible.
You're right.
Okay. Well, thank you, Sergey. I apologize for quizzing you on something from 10 years ago, but I think hopefully people who watch this got something out of it and can understand some of the power of the tools that we use. This is ZMAX simulations and working in the FAR IR. So thanks again for your time, Sergey, and telling us a little more about the work of Optical Engineers. Thanks, and we'll talk to you next time.
See ya. Bye-bye.
Thank you. Bye-bye.